We've taken some time to look at electric fields created by point charges, and now at the beginning of Chapter 18, we'd like to think about what happens when we have uniform electric fields. A uniform electric field means just that the field is uniform, that its strength is the same everywhere. We need to think about what kind of charge could create that field. We know from the previous section that if the field lines are going from left to right, then we must have positive charge on the left and negative charge on the right. So in this case, we have a uniform electric field created by two parallel plates. As a positive charge moves in this electric field, its potential energy changes. So let's consider that for a moment. Here's a positive charge. If I try to move this positive charge to the left, I'm going to have to do work. Why? Because the positive charge is repelled by the positively charged plate. So that work that I do gets stored as potential energy. So the change in potential energy is equal to the work done on the charge. Remember that work equals force times distance. In an electric field, we define that the electric field is equal to force over the charge. So making a substitution, we can say that work equals negative QED. So again, what I've done here is I've taken the second equation, I've rewritten it to say that force equals charge times the electric field, and then I'm taking that and substituting it in here to the work equation. Therefore, the potential energy that is stored when we move a charge in an electric field is equal to negative QED. The negative sign indicates that the electrical potential energy will increase if the charge is negative and decrease if the charge is positive. And this equation only works in a uniform electric field. So what the heck does that actually mean? I'd like you to take this idea of two parallel plates, and again we've got one plate that's positive and one plate that's negative, and what happens if we take it and we rotate it? Now instead of thinking about charges, for just a moment I'd like you to think about gravity. I'd like you to think about this being a room, and we have a ceiling and we have a floor in our room. And if I take, in the gravitational model, if I take a mass, and if I'm holding that mass and if I let it go, it will fall to the floor. So very much the same thing happens in an electric field. We would call the positively charged plate, I think of it as a ceiling, and the negatively charged plate I think of as a floor. And if I were to have a positive charge in that electric field, if I were hanging on to it and then I let it go, it would fall toward the floor. Now what's a little bit strange here is that if I had a negatively charged particle and I'm playing with it and then I let it go, it would fall upward toward the ceiling. It wouldn't go through the ceiling, it would stop here. That does not happen with gravity. Gravity is always an attractive force between masses that works one way. So electricity can be a little tricky because you have to remember that with positive and negative charges we can get two different directions. Let's think again then about what happens as I take this positive charge. It wants to fall toward the floor. But if I quote unquote lift it toward the ceiling or push it toward that positive plate, it's just like lifting a mass in a room. It's like it's giving it potential energy. And then what is that potential energy? It's the ability to do work. So, oops, I got ungrouped here. So if I were to let this thing go, it would indeed move toward the floor. I'm going to take this point in time then to remind you now that we're studying a second type of electric field. We started out studying electric fields caused by point charges, and we practiced drawing them. we learned that positive charges have fields radiating away from them. And remember that these field lines tell you the strength, oops, and the direction of that field. They also tell you the shape, which is more important when we're dealing with two interacting fields. But basically, when I look at these arrows, what it's telling me is if I were to take a positive test charge and put it in that field, the arrows tell me that that positive test charge would be pushed away. The arrows also tell me that when I'm close to the object, the denser field lines tell me that the field strength is more. And as I get farther from the object, the less dense field lines tell me that the strength of the field is weaker. In other words, if I take my proton or my test charge and I move it away, it now experiences a weaker force from this charge. So that's one type of scenario we're studying. Now we're also studying a second type of scenario, and that's electric fields caused by parallel charged plates. I'm going to take this opportunity to redraw the situation because you should practice redrawing the situation so that you know it backwards and forwards. And I'll do it backwards this time just to prove it to you. Let's say that my electric field lines now were moving from right to left. That would indicate that my positively charged plate was on the right and my negatively charged plate was on the left. And if I were to take a positive test charge and put it in this field, it would move to the left. So we can summarize what we've learned so far. The electric field lines around a point charge, they get less dense as you get farther away from the point charge. This indicates a weakening field. And this should make some sense to you in terms of a gravitational model. If I had a planet, if I move away from that planet, then the force, then the force of not going to do it for me here. Then the force of gravity is going to get less as I move away from that planet. Okay. Now let's think about a uniform electric field. In a uniform electric field, the density is uniform. Which means that the strength is uniform. If we go back a couple of slides, just for a moment, to this scenario with a ceiling and a floor, if you imagine a room anywhere in that room, we would say that the Earth's gravitational field is uniform. In other words, if I have a ball and I'm going to drop the ball, I could drop the ball from anywhere in the room and it would fall, it would fall in the same way. It would fall at 9.81 meters per second squared. So I would say that this is a uniform gravitational field because the ball behaves the same everywhere in this room. Very similar with my electric field here. No matter where I put the charge, it will behave the same way when I let it go. So we say that that field is uniform or the same everywhere. Remember that the field is a way to explain the forces that we see, and those forces cause motion. Okay, next let's look at the electric field strength around a point charge and then for a uniform electric field. We've already looked at the electric field strength around a point charge, so you might want to turn back to your notes for a moment. It's based on Coulomb's law. It's kq over r squared. So the electric field around a point charge, again, is kq over r squared, where q is your charge and r is your distance. The electric field strength in a uniform field is just defined as the force on a test charge divided by the test charge itself.